indeed, so I was invited to give here a grand public talk. And essentially today I discovered that this grand public will be 50% of physicists and 50% of mathematicians, plus Monsieur, and and also so the vice rectress of Geneva University, Brigitte Gaillot, that we heard just before, and another one who disappeared, Jérôme. Can you catch Jérôme? It's a third of my audience. Ah, he's there. Jérôme, the dean of the science faculty in Geneva. Okay, so but maybe since indeed the vast majority of you are not really the grand public, it's the good time to, should I also speak in that?
It would be useful, but I can leave it here and probably will work, or you can.
Okay, that's going to be interesting. Okay, it's a test, I guess. Yeah, to quote Feynman, who once said, or is supposed to have said, never underestimate the pleasure an audience experience when understanding something. So since this is a general public talk, now the pressure is on you. You are supposed to understand everything and to enjoy it. So how did all that start? Science. So science started thousands of years ago. There were people here in Les Diablerets, and in the evening they had no TV and no social media. So what did they do? They watched at the stars, the sky, and it is beautiful, no doubt about that. And if you do that long enough, well, first you find it quite random or messy. But if you have more patience and you look at it, you see that there are a bit of regularities. Yeah? You're going to see, for instance, that's the obvious thing, that the moon is orbiting or is raising and lowering. And also you will see some other regularities that today we know are the planets that you can see. So you see some regularities, but you also see what I have shown here with this Brownian motion, something which looks very chaotic, and which also today we understand is pretty well known as the butterfly effect. You know, if a butterfly flies somewhere in Patagonia, a few days later, you have nice weather in Les Diablerets. Okay, so that was the beginning, but that was, of course, not the entire story. There is something else which I believe was very fundamental and essential to trigger science. It has to do with gods. Now, in the old time, the Greeks, they had plenty of gods, very human-like gods. And when one god made a decision, established some rule, then another god would establish a conflicting rule. So no idea of real rules because it was always conflicting, until came this beautiful idea of having a unique God. Okay, maybe like that, never mind. But a unique one. So if you have a unique one, who moreover is the creator of everything, then for sure, he didn't make or create a mess. And that leads naturally to this idea that there are natural or laws of nature. And these laws of nature, they describe regularities, as you see on this slide, with the idea also that the effects follow by necessity from causes. And this idea of necessity and regularity also then led to the next step, namely determinism, scientific determinism. And this is extremely deeply in the public's mind. So you're the public, no, the grand public. So it's all in your mind. And then people, the real grand public, don't really understand all this stuff about, vaccination. Yes, but it's not really sure that I'm then safe. Maybe not. Epistemologists, comment on dit? So people make predictions about this pandemic, but it's not for sure. And then some people say, oh, this is not scientific. Look, it's not for sure. It's not deterministic. Okay, of course, here, I guess we all understand that. But so there is this idea that science has to follow deterministic laws. But still, chaos and the difficulty to predict the climate change, for instance, is still there. No? And we understand it today by saying, okay, there are all these little molecules that bump in all directions. And at the end, the bigger one, the larger one, the red one here, will slowly undergo some Brownian motion. And of course, if you do that on the scale of the planet and the atmosphere, it's really complex. But we will say this is just deterministic chaos. It's the same deterministic laws, very complex. And many people here know enormously about that. Okay, now we jump a bit ahead, and last century, we had revolutions, scientific revolutions. One is relativity, the other one quantum mechanics, and then these great people met and debated, so Bohr and Einstein first, and they debated, is the world really deterministic, or isn't quantum mechanics, after all, bringing in some indeterminacy? And Einstein famously replied, God doesn't play dice. And a bit less known, maybe, is this other encounter also with Einstein and Bergson. Bergson was at the time the most famous philosopher, and his philosophy had a lot to do about time and creative time and becoming, and all that. And there was also this important historical meeting, which Einstein kind of won by declaring that there is no such thing as the philosopher's time. So really, again, determinism was reinforced. But indeterminism didn't really give up. And there is here a nice quote, which I like, from this philosopher, Elisabeth Anscombe, who was a student of Wittgenstein. So let me just read it. The high success of Newton's astronomy was in one way an intellectual disaster. It produced an illusion, for this gave the impression that we had here an ideal of scientific explanation, whereas the truth was, it was mere obliqueness on the part of the solar system by having had such a peaceful history in recorded time to provide such a model. So some people were still opposing to this idea of scientific determinism, but probably you've never heard of that. So what is non-determinism? We all more or less understand what determinism is. What would be now non-determinism? Well, or indeterminism, which is equivalent in my eyes. So it's randomness, so it's unexpected, unpredictable. So for instance, here I have a card. I'm going to flip it. What is on the other side? Is it a king? Is it a queen or whatever? Here it is. So that was probably unexpected to you, except if you have already seen the talk. So what we mean by unexpected or unpredictable is for whom? And true randomness should be unpredictable for everyone. I'm even tempted to say even for nature, it should be unpredictable or unexpected. And also here something changed with the technology, coming back later also. But you know, certifying randomness is still a philosophical problem. It's not easy. We also say it's a mathematical problem, but it's also a philosophical one. But it's also an urgent practical one. We need randomness to do for security, to do cryptography. For all our security, we need it. So here you have actually now an elementary indeterministic quantum process. It's just photons, one by one, that hit this beam splitter. Behind the beam splitter, you have two single photon detectors, one that is labeled 0, one is labeled 1. And you see that outputs random bits. That's what at least quantum mechanics tells us. We all know that, I guess, except maybe, but believe me, it's like that. Okay, so you have these coming out, and in practice it goes faster, but that's the principle. And so you have here really a conceptual simple entropy source, so something useful, which only quantum physics offers. And it's easy to see also where the origin of the randomness comes. It's really this beam splitter combined with the two detectors. So this is a practical random number generator. And so you can now go all the way, let's say from the other extreme, from philosophy to engineering or applied physics, and you put that in a little box. You see the size. It produces millions of these random bits per second, and it has to be very serious. You see, it has even been certified by the Swiss Federal Metrology Office, by the French Army, and it's used in different kinds of applications. Good. But now, how is it, or why is it that physicists, at least physicists like me, so the quantum physicists, are totally convinced that we have true randomness, that is, quantum bits are truly random? And here what I want to do is something that you should never do in a grand public talk. I'm going to prove a mathematical theorem. But don't get lost. I mean, I know most of you should understand everything, but for the others, the main message is that there exists a theorem, that there exists a proof, and even a bit more, that the proof is actually not complicated. Maybe you're not going to understand everything at once here, but it's really not very difficult. And if you're really fascinated, you can still read that book. Okay, so let's have now two of these random number generator here. You know, this beam splitter with the photons arriving one by one. I'm just changing one thing. I allow here an input. I can make a binary choice here, which essentially would be rotating this beam splitter. Suppose it's a polarization beam splitter. I can rotate it. And then I get my output here. Again, these 0 and 1s as I had before. And the same on the other side. And the assumptions, since this is a theorem, you have assumptions. And the first assumption is that distances really exist. So there's a real distance here. What does it mean, this distance? It means that things cannot jump instantaneously from one place to another. No, it's just, this doesn't exist. Things, we can go from here to the Hotel Les Sources, but it's going to take a little bit of time. We cannot just jump instantaneously there because there is some distance. That's the first assumption. The second one is also kind of almost trivial. Namely, there is no superdeterminism conspiracy. So these choices here that they denote with this letter X on one side and Y on the other side, these choices are independent. You can make independent choices. It's not all superdeterministic. Now so these are the two assumptions. Then there is one more thing that comes in the assumption, but which is actually an experimental fact. So we can just test it. So the promise is, oh, I have an equation in a public talk. Should never do that. It's also the only equation you have in the book, by the way. So let me go through this equation. Sorry for the physicists and mathematicians. And it's difficult to make it simpler. So X and Y are bits, 0 and 1. So 0 times 0 equals 0 times 1 equal 1 times 0 equals 0. C'est bon? Okay. And 1 times 1 is 1. Okay. On this side, we add the outputs. 0 plus 0 is 0, 0 plus 1, 1 plus 0 is 1, and 1 plus 1. So 1 plus 1, you would say it's 2, but since we are living in a world of bits, and bits are 0 and 1s, 2 is equal to 0. So we do addition modulo 2 for everyone here. Okay, so this is the promise. And then here is a picture where you see the real distance. So we did this experiment a long time ago, 97. It all started in 97. Just wanted to say, so this is 10 kilometers in B-line. And at that time, we were commuting by bike from one side to the other. So I can tell you there's a real distance. And things don't jump from one side to the other. We feel the distance, really. Okay, anyway, so we do that. And then comes the proof of this theorem. So first, we introduce this conditional probability. You know, the probability of getting the outcomes, the results, A, B, given that we performed the measurement XY. So we oriented this beam splitter accordingly. And here I'm going to, in this table, to fill the table together with you with all these probabilities. So here in this upper left corner is the case X equals 0 and Y equals 0. Then here it is X equals 1, Y equals 0, comes here. And in each of these tables, you have 4 numbers, the 4 probabilities. That's a probability of 0, 0, of 1, 0, 0, 1, and 1, 1. So let's look first in this corner. So 0, X times Y, 0 times 0, this is 0. So if you have 0 here, you cannot have 0, 1, and 1, 0 here, because then the equality would not work. So you must have some zeros here in these probabilities. And it's the same here, it's the same here. Here it is just the opposite, because here X times Y is equal to 1. So that excludes 0, 0, and 1, 1. Okay, so now here we have some probability, P. a number between 0 and 1. And now we are going to use the fact that there is really distance here. Real distance means that if I'm just on this side and I look at my statistics that I observe here, it cannot depend on this x because the value of x cannot jump to the other side. So technically, we speak of no signaling. And so it means that if I now look at this marginal, the marginal on this side, on the right-hand side, this is this sum, p plus 0. And this sum, which is valid now for x equals 0, should be the same as this sum here, valid for x equal 1. It cannot depend on x. Consequently, here we must have p. Now this goes also in the opposite direction. So now I do the argument on this column, going from right to left. And now I do it again, and I do it again, and I get this. But probabilities are normalized. Consequently, p is 1/2. Consequently, I've just proven you that indeed these quantum bits are truly random. This is a theorem. Now, this theorem assumes exact equality here. And I told you this is checked experimentally, but experimentally you never find an equality. You always have some noise. Moreover, to be for the many physicists and others that understand, even quantum mechanics doesn't allow you to do that, but to get close to it. So anyway, then a more complicated proof would allow you to derive these curves here, and you really have for every violation of the CHS-Bell inequality, you get some randomness, some positive randomness, maybe not full. My proof was for this point here, which is clearly the simplest one. Okay, so what you conclude from that actually our world is not deterministic. The universe is open. Nature is able of act of pure creation. So I'm a physicist, and I'm telling you about creation. Because this randomness is really new information that gets created as time passes. A very different worldview than scientific determinism. And I like also to put this paper here, not only to show that, okay, there's some argument by authority, but the first author, Stefano Pironio, who is now professor in Brussels, was actually in Geneva at that time. So I don't know, the one or the two here refers to University of Geneva. Okay, so we have that, and then go back. So that was kind of more fundamental. Let's go back to engineering. You give that to an engineer. No engineer here, I guess. But engineers are really incredible persons. They are able to do the following. They take that and they put it into a chip, which here now has 2 millimeters, super low power consumption. And then you can put it into a smartphone. You can guess the trade here. Unfortunately, you can buy these smartphones today only in Korea, not yet in Europe. But it's coming. And it's coming like all quantum technology you heard about, quantum computers, quantum cryptography, quantum whatever, sensors, and so on. And these devices will have in them randomness of the sort I just presented to you. So my bet is that these quantum technologies will bring into people's mind the idea of scientific indeterminism. Today, scientific determinism will probably, our kids will be playing with that as babies, and I guess they will learn about scientific indeterminism. But so what about regularities? There are still some regularities. The moon is still super regular. I mean, eclipse and all that we can predict and retrodict, and okay, stones and whatever falls down as it used to. And so clearly not everything is indeterministic. Order cohabits with randomness. And in particular, what now about this scientific, this deterministic chaos? What about deterministic chaos? So the way we do that in general, we represent that. We say, okay, actually there are these initial conditions, there are deterministic equations. And so in principle, at least nature is able to solve these equations and make all that evolve in a deterministic way. Okay, we talk about this hypersensitivity to initial conditions, and that raises now the status of initial conditions. What are initial conditions? So generally, we represent initial conditions by real numbers. Okay, so let me show you a typical real number. Here is a typical real number. This one happens to start with a 0. That's not so important. Then comes the dot, and then you have digits. And you have digits. And these digits have no structure. If it's a typical real number, has no structure. They just come and come and come. And it goes on. And okay, if we have enough patience, at some point, the slide will be full. But it will continue. It will go all the way to Australia, out of the solar system. When we all be dead, the process will continue. In 1 million years, the process will still be continuing. There is really infinite information herein. Now, this is really actually my intuition of real numbers. I don't know about you, so we could make a pool maybe afterwards. Because the real way classical mathematics describes a real number is quite different. Classical mathematics says the following. Careful. Everything at once. Ta-ta! Here it is. Everything, infinite information in 0 time. That is the mathematics that you are all using, or we are all using. Yeah? It's an enormous assumption to think that we can get infinite information in 0 time. But that's the way we do it, usually. And so here what we are saying with this classical mathematics is that instead of indeterministic events happening as time passes, which is the intuition of everyone, all the indeterminacy is coded in the initial condition. That's why we can talk of deterministic chaos. Or another way of saying that, instead of Einstein's God playing dice as time passes, God played all the dice at the Big Bang and coded all the outcomes in the initial condition. So you start seeing here that it seems that it's the mathematical language that we use that forces us to speak of deterministic chaos. And if we switch to another form of mathematics, intuitionistic mathematics, that was developed completely independently of all that, what I'm saying here, we come to the conclusion that the mathematical real numbers are not physically real. Or, okay, now, the slogan is real numbers are not really real. That's the title. No, it's not on this page. Okay, and Carl Possi, who is one of today's master in intuitionistic mathematics, he wrote this book, which is probably the only accessible book, in my opinion, on this subject. So he wrote, there is no infinite helicopter allowing us to survey the whole terrain or to tell how things will look at the end of time. So you see, you could have this vision that there is a terrain with roads and bifurcations, and you have choices, and you make your choice. And of course, if you have this God's eye view, you see everything. You see how it goes. You see how to go to the Hôtel des Sources and wherever you want. Or also, if you wait until the end of time, assuming such a thing exists, of course, then at the end of time, all this real number, my intuitive real number, has terminated. So then it's back to standard classical mathematics. And here I think this is a very interesting example. Climate physics. Everybody knows this is super important. Tim Palmer is one of the leading physicists, climate physicists in the UK. And he wrote this paper, well, maybe co-authors, I don't know. How do they do it actually? In principle, they should put into their computers where they, with which they simulate the future climate, they should put the exact initial condition of every air molecule on the planet. Of course, impossible. So they just put some approximation. And then they let the simulation run. But this is a chaotic system. So pretty quickly, they run out of the digits. You know, it's the small digits that become the relevant one. So what do they do in real practice? They add stochastic reminders. So they do exactly the stochastic thing. They use maybe not a quantum random number generator, but some generator that produces these new digits that they feed into their simulation. So actually, without knowing, they are doing intuitionistic mathematics. Actually, everybody doing anything on a computer, the computer is finite, so it has to be more like intuitionistic mathematics, and it can certainly not be standard classical mathematics up to some approximation and so on. Okay, so also one consequence of this is that statements about the future can be neither true nor false, but indeterminate. So the law of the excluded middle does not hold. If I make the statement, it will rain in exactly 1 year time at Piccadilly Circus. If you believe in indeterminism, this cannot be true because it is not certain that it will rain, and it cannot be false because it is also not certain that it will not rain. We just don't know. It is indeterminate. It's not only that we don't know. If you believe in indeterminism, also nature doesn't know. It depends what kind of new information will be produced in the meantime. So it's really the mathematical language we speak that has this huge influence on the worldview that physics presents to us. And so in the conclusion, I'm essentially repeating all that. Maybe one important point, so science and physics started with strong determinism. Modern science is more and more friendly to randomness. However, this randomness, it's not a mess. It's randomness with probability laws, as we know very well from quantum mechanics, and also from statistical mechanics and all that. No, you have strict probability rules. Yeah, the mathematical language we speak when talking physics impacts our worldview, and some conclusions one is tempted to infer from physics, like determinism and the illusion of time, are actually inspired by the mathematical language, not by the facts. Thank you very much. I hope you enjoyed it according to Feynman. Thank you.
Thanks a lot. Any questions or comments?
Maybe just some. The Schrödinger equation is a deterministic equation, right? So the wave function evolves deterministically. Only once I make an experiment or want to compare interpret this wave function as the outcome of an experiment comes the randomness. Right?
Do you see any Schrödinger equation here?
No.
You don't need Schrödinger equation. This is one of the beauty of quantum information science. You can do everything because you're absolutely correct. I mean, everything you said, of course, is perfectly correct. But what I want to add to that is that here you see everything is done with this input. This is a classical input. It's just a bit, a 0 and 1. It's how you rotate your polarization beam splitter. This is the result of your experiment. This is something, it's, I don't know, a flash which is either red or green. Or Daltonian will not understand it, but you know, it can be a sound which is either one or the other. It's something that you can really feel. And so this is really, again, something classical. The same on this side, Y and B. All that is totally classic. You can forget Schrödinger equation.
So you want to say Schrödinger equation isn't useful?
I'm not saying it's not useful. It's not useful for this application. You know, Schrödinger equation is not useful for absolutely everything. But for this here, for proving this randomness, you don't need a Schrödinger equation, indeed. And I think this is indeed something absolutely remarkable that with this, okay, it all started with Bell inequalities, but going beyond that, there are many results that you can get forgetting completely Hamiltonian Schrödinger equations. Not saying that Hamiltonians we should forget, but for this specific application, you can forget it. It comes under the technical name of device-independent quantum information processing. In our community, Renato, myself, that's the way we talk about it.
Any other questions?
There's an online comment from you who says that the blue gentleman in the picture with Einstein is not very simple.
I don't think so, but okay. Thank you, Jörg. I will check that, of course. I know which one. Yeah, I'm pretty sure this is Bergson, but I'll send you an email.
No, it is Max Planck. when they received the Planck medal. It's nothing to do with Bergson.
Maybe just a comment on what you said about this weather predictions. So maybe you said that, but couldn't say that actually any computational physicist, also in quantum computational physics, should actually think in these intuitionistic terms, because we are always forced kind of truncate the numbers. I mean, there's no way you can kind of deal with the real numbers in the way you describe them as an infinite information.
Yeah.
So in a way, any computer scientists should appreciate that view. Is that somehow?
Yeah, I think I said it, but maybe too quickly, or maybe I forgot to say it. So thank you for. But indeed.
Does this community think in that way? Because there's a whole community
Yeah.
be forced to think in that.
I don't know, you know, I mean, all these results about this intuitionistic thing is quite recent. So I don't know yet how deeply it went into this community. I don't know. But you're right. I mean, if you go to a computer, you're doing intuitionistic mathematics.
Whenever there are measurements, the Schrödinger equation does not apply.
Yeah. So, but I agree. And indeed, again, I said, I mean, that's the same comment as I made to Ruth. You don't need a Schrödinger equation. You can have it in the back of your mind. But for this specific, and only for this kind of specific application, you just don't need it. You can do everything with these classical inputs and classical outputs. Ah, yeah.
So, what is the perimeter of this randomness? Is it finite or infinite?
Finite. It's finite.
Okay. Okay.
No, it's finite. Can go very fast, like this commercial thing. It's megabits per second, but a megabit, so millions of bits, is still finite.
I've got a somewhat philosophical question. So you were speaking about determinism and indeterminism. And of course, there is a philosophical question related to it, the one of free will. So I don't know, right? Maybe one question is, so do we have free will? I hope we do, but of course, I don't know. And then do we need quantum mechanics to have free will? Or like, because right, it also depends a little bit on this randomness concept.
Yeah. So in my opinion, determinism is incompatible with free will, but this is highly debated. But also randomness doesn't explain free will. So randomness is, I believe, maybe useful for free will, but it's certainly not an explanation. So I don't think I have any explanation of free will. I don't think science has anything to say on free will today. Maybe it will have something to say someday. But as of today, we can, I'm already very happy that we can introduce in an elaborated way this indeterminacy and randomness into science, but don't jump to free will from there.
No more questions, then let's thank Nicolas.
Thank you.